Today we're going to take a look at some special cases of right triangles and review the algebra needed to solve for missing sides on a right triangle. Let's get started. To begin, let's recap the features of right triangles in general. Of course, we're looking at a three-sided closed figure, a polygon, which has three interior angles which sum to 180 degrees. In the case of a right triangle, we have one right angle measuring 90 degrees and two acute angles which sum to 90 degrees. One of the most famous equations in the world of mathematics is the Pythagorean Theorem, which relates the side lengths and the hypotenuse of a right triangle. In this relation, we see that the legs, labeled A and B, are across from the acute angles in the right triangle. The legs intersect and form a 90-degree angle. Across from that right angle, we have the hypotenuse, which is labeled C. The Pythagorean theorem can be used to find a missing leg or hypotenuse measurement for any right triangle. Let's practice using it. Below, I have 8 squared plus 3w quantity squared equals 5w quantity squared. Following order of operations, I'll go ahead and apply the exponent on all terms. I now have 64 plus 9w squared equals 25w squared. I can subtract 9w squared from both sides of the equation, resulting in 64 equals 16w squared. I'll divide all terms by 16, simplifying the equation to 4 equals w squared. This means that w can be positive or negative too. Since we're looking at geometric measurements, we'll take the positive solution, and that makes w equal to 2. Replacing w equals 2 into the measurements of the triangle, I have 2 legs, 8 and 6, and a hypotenuse, 10. Alright, after using the Pythagorean theorem a few times, you may begin to notice some patterns. I want to briefly point out what are referred to as Pythagorean triples. That is, a set of 3 non-zero integers that satisfy the equation a squared plus b squared equals c squared. Only the first 4 triples are pictured here. However, there are infinitely many triples. Here are a few other fun facts. There will always be one even number in the trio. C will always be odd, and prime numbers like to make an appearance. These are often worth memorizing because they pop up on the SAT in similar standardized tests. One last thing, make sure you keep an eye out for similarities. The 3, 4, 5 triangle pictured here has been scaled up by a factor of 2. It is still a Pythagorean triple, just dilated. In fact, if you take a look back at our previous example, you'll see it's the very same 6, 8, 10 Pythagorean triple. Let's look at 2 more special cases. The first of which is the isosceles right triangle. This is commonly referenced as a 45, 45, 90 right triangle. You have 2 congruent legs, each across from a 45-degree angle. Then you've got the hypotenuse across from the right angle. Using the Pythagorean theorem, we can show that the hypotenuse will always be the side or the leg length times the square root of 2. Since all isosceles right triangles are similar, this ratio will be constant. The second special case we will look at is that of an equilateral triangle that has encountered a perpendicular bisector. After slicing the equilateral triangle perfectly in half, we generate 2 30, 60, 90 right triangles. Here is one of those up close. Our 2 acute angles are 30 and 60 degrees. Across from the smaller 30-degree angle is the shorter of the 2 legs. Likewise, across from the larger 60-degree angle is the longer of the 2 legs. As with all right triangles, the hypotenuse lies across from the right angle. The shorter leg is designated s in this ratio, followed by the longer leg, which is designated s times the square root of 3. Finally, the hypotenuse will always be twice the shorter leg. Again, these ratios are constant because all 30, 60, 90 right triangles are similar to one another. Before we go, I want to solve a few of these triangles with you using the ratios we just looked at. First, on the left, we are solving for the hypotenuse of an isosceles right triangle. According to our facts, the hypotenuse will be the leg times the square root of 2. So this will be the square root of 3 times the square root of 2, or just the square root of 6 simplified. On the right, we're solving for the hypotenuse of a 30, 60, 90 right triangle. We are given the shorter leg. We know that it is the shorter leg because it lies across from the smaller 30-degree angle. According to the ratio we saw, the hypotenuse will be twice the shorter leg. So on this triangle, that makes x equals 4. Let's look at just 2 more. On the left, we're solving for the shorter leg of a 30, 60, 90 right triangle. We are given the longer leg, which is across from the larger 60-degree angle. We know from our ratios that 6 equals the shorter leg times the square root of 3. To solve for x, I'll divide both sides of the equation by the square root of 3. Then I'll rationalize the denominator by multiplying by 1 in disguise. That is, the square root of 3 divided by the square root of 3. This allows us to write an equivalent fraction with no radicals in the denominator. Our simplified answer will be 2 times the square root of 3. Last, we solve for the leg of an isosceles right triangle given the hypotenuse. We know from our ratios that the hypotenuse, 1, equals the leg times the square root of 2. So we have 1 equals x times the square root of 2. We'll divide both sides of the equation by the square root of 2. Then we'll rationalize the denominator. Simplifying, we have root 2 over 2. That concludes our quick review of special right triangles. Make sure to use the additional resources provided on our course page for further examples and practice. Thanks for watching.